Okay, we're going to review Dr. Ari's problems for inductors and capacitors. So I'm just going to start at chapter problem 7.1. And for this, I'll be annotating on the right-hand side. So let's look at this. The switch in the circuit has been open for a long time. Okay, when we see this, it's been open for a long time. What comes to mind then is then I have to be thinking about what is the circuit before t equals 0. So looking at this circuit diagram here, I'm going to do one for at t is less than 0. And when I do that, I'm going to draw out what the circuit is and calculate any voltage drop that is either on this inductor or the current that might be going through it. And then I'll do one at t equals 0 and then at t is greater than 0 diagram for that. So determine, looks like for part A, I is 0, I at 0, so the current at time equals 0, and the current at time equals infinity here. Okay, one special thing about inductors we know is, I think that Eli, because voltage is used for the E, is equal to inductance times di dt, and therefore the current can't change instantaneously. So we know when the switch closes at time equals 0, the current can't change instantaneously. So therefore the current before, when it's right before approaching 0 from the negative side on the number line, is equal to the current approaching on the positive side, because you can't just jump the current all of a sudden. Like it can't be a jump like this at time equals 0 when the switch closes. That can't occur. The current has to change over time. So therefore, it will slowly change on a continuous. So like a waveform, it will slowly go. It can't, something like this, it will slowly change. Okay. So let's do at time is less than 0. Our circuit is going to look something like this. So we're going to have our voltage source. We're going to have one resistor here. We're going to have one resistor here. We're going to have an inductor. And then we're going to have one resistor here, and then one resistor here. And here we go. And I'm going to label these. So what we have here is at time is less than 0. This is going to be our 16 ohm, our 12 ohm, and then our 4 and our 8. And so what we can see here, and then our inductor is 80 millihenries. What's going to be happening before time is 0 is that we can draw an equivalent circuit for this. So we have our voltage source, same thing. And those 4 resistors, they're all in series. So we can just make one large resistor and we can make an inductor. And so combining those, I get 16 plus 12, which is 28, plus 4, 32, plus 8, that'd be 40 ohms. And then I have 80 millihenries on my inductor. And so if we know an inductor, the two main takeaways is an inductor does not want a change in current. But over time, an inductor becomes a short circuit. Because if we look here, the current will just be staying the same over time. So since the current is going to be staying the same, we know in this equation for an inductor, let me do it in a different color. So for our inductor equation, if the current is constant, that means this will be 0, and therefore the voltage across the inductor is 0. If there's 0 voltage across this inductor, it's going to act as a short circuit, because that means there's no voltage drop. So there's no like type of resistive, no inductive element at this point. So it's just going to be a short circuit here. And so we can redraw this diagram. So it's just going to have our voltage source and the resistor. And because that inductor became a short circuit with time, since there's been no change in current, it's been in this position for a long time. That's what it set up here before the time was 0. And so here I have my resistor, which is 40 ohms. Here I have my voltage source, which is 20 volts. And if I do 20 volts divided by 40, that's going to give me 0.5 amps. So right here, I'm going to do 0.5 amps is going through the circuit. And since we have 0.5 amps for the circuit, that is going to be our I of 0, since this part is not connected. So that's the same current throughout. And so we know I of 0. So because I of 0 right before is equal to I 0 right after. So when that switch is connected, it's exactly the same because the inductor will not allow there to be a big change in current because the current before has to equal the current after. And then I, as it is infinity. So now we need to do another diagram. So that's what I think about here. So let me draw another one here. And this one's going to be at time is greater than 0. So at t is greater than 0, what is the circuit going to look like? So I can find out what I need to get for my current value. Well, the inductor, if this switch has been then closed for a long time, we know that the current then won't be changing that much. So this is just going to become a short circuit because the current will have already changed, because at time infinity, that's a long time that switch has been closed from time 0. So what our circuit's going to look like is, I told you guys, whenever it's a long time, the inductor becomes a short circuit. So here we're going to have that 16 ohm, and then that switch is closed. And then here's our 4 ohm resistor down here. And then we have the 12, and then the inductor becomes a short circuit with time. And then we have our 8. And so I'm just going to recombine these to make it a little simpler for us. And so we're going to have the one circuit here. And then since we know here, we have our 16 ohm, we have our 12 ohm, we have our 8 ohm, and we have the 4 ohm. If you were an electron and you were going for the circuit right here, would you go down or would you go to the right? You would take the path of least resistance. So you would then go down here, down this way. You wouldn't go to the right, correct? Because there's a resistive pathway. And so that's the interesting part is, therefore, at time infinity, it's going to be 0 amps here going to the right, since the electron will want to take the path of least resistance. So it's going to go downwards because there's 20 ohms of resistance here and there's 0 ohms. Do the calculation. 0 times 20 equals 0 all over 0 plus 20. And so 0 ohms of resistance, that means the equivalent would be 0 here if you even did that for this combination. And so we have that 16, and then we have the 4 ohm resistor, and those combine to produce the 20 ohm resistor. So I have my voltage source here, and then I have my 20 ohms. And therefore, you can notice that the current now that's going to be going for the circuit is, of course, 1 amp. However, that 1 amp is through, if we look here, because we have 1 amp, 20 divided by 20, 20 volts divided by 20 ohms gives us 1 amp. All that current's going to be going through this path. None of it's going to be going through this path. So this is where the 1 amp is. Therefore, there is 0 amps going in this direction. And since there's 0 amps going in that direction, that's what it's wanting. It wants I of 0, and we notice I of 0 is through that path. So there's 0 ohms at time infinity here. So we got for I of 0, we had 0.5 amps. And then at time infinity, the current was 0 amps. So I'm going to write that right over here. So our I of 0 is 0.5 amps. And the I of infinity is going to be 0 amps. And then it says determine I of 0 for time is greater than or equal to infinity. Well, there's an equation for this, which is really good to memorize. I definitely suggest you guys need to know it. The equation is, for this part, I'm going to put it to the left. It's x of t equals final value plus initial value minus final value, and then times e to the negative t divided by tau. Let me put that in a better color. Okay, let me just put it down here. Okay, so this is important, this equation right here, because it's the final value plus the initial value minus the final value, e to the negative t over tau. So let's look at how we can find that. So I'm going to plug in, we need to find current. So for a current, I'm going to just write that below. I of t is equal to the final value, which we determined was 0 amps at time infinity, plus the initial value, which was 0.5 amps, minus the final value, which was 0 amps, times e to the negative t all over tau. And we just need to calculate tau in this circuit. Well, if you guys remember, tau for an inductor in the circuit is L over R. And so let me draw that out here. We know in a circuit that tau is equal to L over R. And looking at our circuit, we know the inductor value is 80 millihenries. They gave us that right here. 80 millihenries. And divided by the resistance that the inductor sees within the circuit. And so if we're looking at this, trying to determine what it could be, we know that the inductor, how am I going to say this? The best way is the inductor, what it sees beyond here. I'm going to draw the circuit new. So when you're calculating the time constant, it's what the inductor sees. So the inductor is going to see the resistance values. So here, here, and I'm going to draw my inductor here. Other resistance. And then it does not see the source. That's one important thing. And it's at time greater than 0, it said here. So the switch is closed. So up here, it's 12 ohms, 8. Here we got 16. And down here, we got 4. Sorry, this is getting a little messy. So the inductor, what resistance does it see? Do not take into account the source, because the source sees the resistance. The source doesn't see the inductor doesn't see the source. And so here, when we're calculating the equivalent resistance that the inductor sees, so this is where inductor is, it's 80 millihenries. What we have to do is we have to calculate the equivalent resistance. And so here, if we notice there's a short, so the inductor, if you do this combination here, is 20. And right here it's 0, do the parallel combination, that will become 0 here. So the inductor isn't going to see any of these, because it's just going to see that there is 0 resistance through this path right here. So 12 plus 8, the inductor sees 20 ohms here. And so 80 millihenries divided by 20 ohms, that's going to give me, do that in my calculator, 80 e to negative 3 divided by 20. I see 4 milliseconds. So that's my time constant. And so for my time constant tau, I'm going to plug that in here, divided by 4 milliseconds. Okay. And now that was my equation. I told you guys you need to know this. Final value plus initial minus final times e to negative t over tau. And so when I set those equal, what I get for my equation, I get I of t is equal to 0.5 e to the negative t divided by, when I do 1 divided by 4 milliseconds, what I get is I get 250 just in the numerator t. I just simplify 1 divided by tau, and that gives me 250, 1 divided by 4 milliseconds. So this is what I get for t is greater or equal to 0. And so that's my value that I receive here for part C. So that's what I got, sorry, part B. And so number C, how many milliseconds after the switch has been closed will I of 0 equal 100 milliamps? And so that's the equation we just got in part C. plug in 100 milliamps to that equation I just wrote. And when I do that, for the left-hand side, so how I would set that up is, let me just do this in a different color. 100 milliamps is equal to 0.5 e to the negative 250 tau. Sorry, e to negative t. Oh yeah, sorry, I just forgot that negative sign right in that equation, so sorry. And what you need to do, you guys, is when you solve this, just take the natural log that will cause it to cancel. So take the natural log of both sides because that is dividing by. So let me just first do 100 milliamps, e to negative 3 divided by 0.5. I get 0.2. So right here, I get 0.2 is equal to e to the negative 250t. And what you need to do is you need to take the natural log of both sides. So that's going to cause that one to cancel. So natural log 0.2 is equal to negative 250 t. And therefore, when I divide by negative 250, so natural log negative of 0.2 divided by, and then negative 250. What I got for my time was 6.4 milliseconds. And that was what I got for part C. So I got T is equal to 6.4 milliseconds. So that's how you solve question 1. Okay, let me look at the question. Sorry, I know I avoided that. What is I infinity? Okay, that was at time infinity. Hopefully that makes sense. I know this got a little messy. Don't worry, next problem, I'll make it look a lot better. But those were the answers. So for part A, we had at time 0.5 amps, and then at time infinity 0 amps. Part B, we got 0.5 e to the negative 250t for t is greater than or equal 0. And for part C, t is equal to 6.438 milliseconds. Okay, I'm going to do 7.4. If you guys are confused on a problem, just drop it in the chat and then I'll do that. I'm just going in order of what they give, but I can switch it up. Okay, 7.4. The switch in the circuit has been in position 1 for a long time. At t equals 0, the switch moves instantaneously to position 2. Find the voltage at the initial value for t is greater than or equal to 0. Okay. What I'm seeing right here is whenever it tells me to write an equation for it, remember what's going through my mind right now is that x of t is equal to the final value minus plus initial value minus final value times e to the negative t divided by tau. That should be going through your mind as well when it says write an equation for when t is greater than or equal to 0 and it gives you no value determined for t. You should be like, I'm going to have to write an equation, so I have to find the formula for it. And so we need to find the final value and the initial value here. We have an inductor in the circuit. So I'm already going to the equation. When I see an inductor, I'm like, okay, I'm thinking Eli, where the E is going to be the voltage, because that's another way you can represent voltage with an E. But I know the current can't change instantaneously. Therefore, because then the derivative would be equal to, if you change it very quick, it's a discontinuity, you know, like if it just steps all of a sudden, it has to be continuous. So here, what I'm thinking when I see this is I know that for the value of I at the point right before 0 has to be equal to the point right after. So E approaching from the positive side of 0. And so that's what I know here. And so let's see, the switch in the circuit has been position 1 and it says for a long time. And so it has been connected the circuit like this. So this part has not been connected. So it's been an open circuit right here. And then at time 0, it connects. And so it comes down here. So let's do it before time is equal to 0. And then let's do it at the time is greater than 0. Because it's saying find the voltage for t is greater than or equal 0. Okay. So what I'm going to be doing right here is for t less than 0, I'm going to make 2 diagrams. One when it's less than 0, because it's been in that position for a long time, and one when it's greater or equal to 0. So here when I do t is less than 0, and this is what you need to be doing for each problem. You need to create 2 diagrams. We have our voltage source here. So voltage source is 90 volts. And then we have a current 13 ohms here. Then we have this 12, and then we have our inductor. And then we have another current source here. Another current, resistor, and then connects back to this side. So let me label those. So here we got a 13 ohm. And then at this point over here, we got a 12 ohm. And then over here, we got 36 millihenries. And then here we got 6 ohms. Here we got 30 ohms. And that's pretty much the summary of our circuit. So I noticed this 13 and 12 can combine. So let's just do that real quick for quick math here. That'd be 25 ohms. And then we got these 2 right here. And remember, it's been in this position for a long time. Therefore, there's no longer any change in current. So we can say the inductor became a short circuit because the change in current, since it's been a long time, the current has steadied out. And therefore, this inductor is a short circuit here at this point. So now we can combine the 30 ohm and 6 ohm resistors that are in parallel and add that to this equivalent 25 ohm resistor, since those 2 were in series up there. So when we do that, our equivalent circuit here, if we're going to try and calculate it, it's going to be 1 resistor. So do those 2, the parallel combination, 30 times 6 divided by 30 plus 6, and then add that to 25. When I do that, what I get is 30 ohms. So I got 30 ohms here, everyone. And then for my source, I have 90 volts. Okay, so that means the current going through is going to be 90 divided by 30. That is 3 amps. So I have 3 amps going through my circuit here. Woohoo, 3 amps. And so I'm going to backtrack. That's what I like doing, everyone. Backtrack everything. So we know that's the current coming out of the source, this 3 amps here, correct? And we have a 25 ohm resistor here. So 3 amps times 25 ohms. That gives me 75, if we think about it, 75 volts is therefore dropped across here. 75 volts is dropped across this point right here. So I'm just going to write above it 75 volts is dropped at this one part right here, because 3 times 25 ohm, sorry, let me label that with the ohm symbol so you guys understand it. So 3 amps times 25 ohms, that means there's a 75 volt voltage drop here. That means the rest of the voltage drop, because the source is 90 volts, that other 15 volts must be dropped across these 2 resistors that are in parallel here. And remember, a parallel combination has the same voltage drop. So here it has to be 15 volts. And so for V of 0, remember, it was the 6 ohm resistor. And so therefore, it must be 15 volts initially. Let's see. If it's 15 volts right then, we know the current, the change in current. Yeah, okay. So we know right here, it's going to be 15 volts initially, and then what, so I'm going to just put here V of 0t. I'm going to say initially. So I'll just say V of 0, the original, not, is going to be 15 volts across that 6 ohm resistor. Now we have to find the final value here. And so the final value, what we're going to do is that's when the switch has been in position 2 for a long time. And so I'm going to draw another diagram here on the right-hand side when t is greater than or equal to 0. And so what that's going to look like is we can disregard this part because the switch is closed here. And so therefore, our circuit is going to look like this, where we have the 8 ohm, we have the 30 ohm, we have the 12 ohm, and then we have the 36 millihenries and the 6 ohm resistor. Okay, so let's just do a combination of resistors. These two, of course, are in series, the 8 ohm and the 12 ohm. So 8 ohm and the 12 ohm. And then this one over here, the 30 ohm, that will become in parallel with those two added together. And then we have this 6 ohm here. And then our inductor was 36 millihenries. Okay, so let me do the combination of that circuit. So when you do the equivalent circuit, what you should get is you should just get your inductor. And then one equivalent resistor. And therefore, when I did this, when I did 20 times 30 divided by 20 plus 30, and then I added the 6, my equivalent resistor I got was 18 ohms. And this was 36 millihenries. Yay. Okay, we got this decided. So now let's think about it. What's going to happen with this circuit? Well, we want to find that voltage drop like for that final value. And we're sort of looking at it and we're like, okay, an inductor over time, all that energy is going to be dissipated to this 18 ohm resistor here. And what I'm looking at is I'm like, okay, the voltage at time infinity, what is that going to be? Will there be any voltage drop? And so what I'm looking at in the circuit is I'm like, will there be a voltage drop across the 6 ohm at time is infinity? And so if we think about it, inductor doesn't like to change its current much, but we had going through it a current of, let's see, if we had 3 amps here, I'm going back to the circuit over here just to know initially how much current was going through this inductor, because then that will determine our current change. So if I'm looking at this, if we do current division here, we have 3 amps coming in and the resistor we're not interested in. So finding this one right here, how much current is going to the right, that's going to be the current coming in, which is the 3 amps times the resistor we're not interested in, which is at 30, all over the resistor we're not interested in, plus the other resistance, which is the 6 ohms over here. And when I do that, 3 times 30 divided by 30 plus 6, I get 2.5 amps going there in that top to the right. And so here I get 2.5 amps here. So we know initially through that inductor, there's going to be 2.5 amps because it doesn't like a change in current, the inductor equation, if we remember. So the current before is going to be equal to the current after. So initially, there's going to be 2.5 amps going through the circuit. And we know there's no source supplying that current. So it's eventually going to run out and be 0 amps. And so eventually this 2.5 will become 0 amps here. So there's not going to be any current going through at time is infinity. And so what's going to happen is there's going to be 0 current. So within this, if there's 0 current, therefore our final value will be 0 volts across the 6 ohm. So what I'm going to do is I'm going to show, let me erase this right here and say this is at time equals 0. So you guys understand better. And therefore there was 2.5 amps going through. However, at time is infinity, there's no source in here, so that current's going to run out, we know. So at time is greater than 0, so once it goes to infinity here, there's going to be no more current, so 0 current, and it's just going to be the resistance. So nothing's going to be happening in our circuit. And so if we backtrack it and there's no current, therefore, within this original diagram, there'd be no voltage drop across the 6 ohms since there's no current going through it. And so we know the voltage at time infinity, so I'm going to put V at infinity is going to equal 0 volts. And so we were able to successfully determine here, since we know at time 0, the value of the voltage was 15 volts. Since there was 2.5 amps going through there, so there was 2.5 amps going through here, times that by 6 ohms, that's going to give you your 15 volts originally, since we found the current before, because the current doesn't change from before and after. When you flip the switch, the inductor keeps it the same because it can't be a discontinuity. There's a derivative here. And therefore, that's how we got the 15 volts. At time was infinity, however, there was no source anymore since we disregarded this section over here, and the current would slowly come out of this inductor, and it would soon become 0 amps. Since there's 0 amps, there's no voltage drop across the 6 ohm resistor because there's no current. So the value of voltage at time infinity is 0 volts. Plugging that into our equation here, the final value is going to be our 0 volts. So let me draw this down here for x of t. Let me just write it down here where there's some blank. The final value of v of t is going to be 0 plus initial, which the initial was 15 minus 0, and then times that by e to the negative t over tau. What's tau in this instance? Tau is going to be what resistance the inductor sees. So it sees everything in the circuit. If we look here, it's at this 90 volt source. And this is when time is going to be greater than or equal, because remember it said right here for time is greater than or equal to 0. And so therefore it's going to see this part. It won't see anything over here. So if we did this, work from the outside, so 12 plus 8 is 20, we know, and 20 ohms in parallel with 30, what that gives us is 20 times 30 divided by 20 plus 30. We get 12 ohms, and 12 plus 6, that's 18. So the inductor sees 18 ohms of resistance. So if we do our tau is equal to L over R, that's going to be 36 millihenries divided by 18 ohms of resistance, what the inductor sees. And dividing that, what I get is 36 e to the negative 3 divided by 18. I got 2 milliseconds. And so here in my equation, I can put for tau is 2 milliseconds. And then when I simplify that, just 1 over 2 milliseconds to get a proper number in the numerator. When I simplify this equation, V of t is equal to 15 e to the negative, that'd be 500 t, and then for t is greater than or equal to 0. And that's the equation I got here. And so that is how you solve this problem 7.4. I know that was a little confusing, but it's the same implication. What you guys need to do, just remember this formula up here. That's literally your main one, the final value plus, and then initial minus final times e to the negative t over tau. And then you look at time is less than 0. Then you can look at time is equal 0, and then time is greater than 0. And then you can, once you look and understand what's happening in the circuit, find your final value, which is when it's infinity, and find the time equals 0, the initial. Calculate your time, tau. And when you calculate tau, that's L over R. So what resistance does the inductor see within the circuit? and then plug it into the equation, and then that's how you get V naught.
Yo,
Hopefully that
Brian,
makes sense.
for tau, for your ohms, you did 12 plus 8, right?
What I did here is I combined these two, 12 plus 8, because remember, this is shut now, so it's only seeing this. So
Yeah,
that's
so shouldn't
20.
it be 20?
Yeah,
So you
and
put
then I did
18
the
ohms.
parallel combination here. So I do 20 in parallel with 30, and that gave me 12. And then I did 12 plus 6, and that gave me 18. Does that make sense?
Yeah, thank you.
So I just simplified the circuit. That's how I got it. Okay, let me look. I think someone had a question they dropped. So why is it 0 though? So it's 0 when there's no sources connected after said time. Oh, are you talking about, yeah, because think about it, Joaquin, let me show you. If we have an inductor here, and then we have a resistor, and say initially this inductor had 2.5 amps, like in our problem there. And remember the inductor's equation, voltage is equal to L times di dt. That's defined the voltage of an inductor. We know an inductor, the current can't change instantaneously, so it's going to slowly drop. If you remember, sort of, it's going to be initially 2.5 amps. And over time, it's going to decrease. And so that's what's happening within our circuit. Since there's no other source supplying, this inductor, therefore, will be slowly decreasing the current because it can't instantaneously change it to 0. So over time, we know the inductor is going to lose the current across it. So if we have our graph here, because there's no supply giving it, this 90 volts is what was giving the current throughout the circuit, and that's what allowed there to be 2.5 amps in this direction here. However, that inductor, once it's shut off here, there's no more connection to that source here. And so the only source that's providing it is this inductor until all that current is drained out of it, because it can't change this instantaneously to 0 amps once you shut off that source, since there's a derivative here. And a derivative, you can't change it like that because that's a divide by 0 error. And so that's why it slowly drains out of the circuit. We saw with that when we calculated the equivalent resistance was 18 ohms. And so slowly it will become 0 amps. And the capacitors, it's a different equation. So let me do that real quick. So let me get off this mode. So for a capacitor, it's a little different because it has, if we have a capacitor here and we have a resistor. Remember the capacitor equation, ICE. And so ICE, I equals C, and then dV dt. And so the voltage can't change instantaneously. So the voltage across the capacitor can't change instantaneously. So what we know, therefore, is, let's say if we had like 5 volts or something, it's going to take time for that voltage, for the charge to come off. And so remember, capacitors are sort of how I think of them. They are like supplying power like a backup generator. And so it's slowly going to die out, that voltage. And so we started at 5 volts here, and it, with time, as t approaches infinity, it's going to become 0 volts because it's going to come off, and that voltage will slowly over time, it's going to give off. And that's the same if the voltage is going to be decreasing, therefore we see with time it's eventually going to become 0 volts in the end. So remember, I just think of ICE, Eli the Iceman, and just for the E put in the V for voltage. And so that's how I can see which one's going to change and how's it going to change over time. And I noticed that the current can't change instantaneously, so it's going to slowly drop, and the voltage can't change instantaneously either, so it's going to slowly drop. Okay, hopefully that made sense. Okay. Let's do a problem. Does anyone have any they want to do? Because I can do one that everyone's confused on, if that would be better. Or I'll just continue if no one has. Okay, looks like I'll just continue. I think the next one is 7.21. Okay, looking at this one. The switch in the circuit has been in the left position for a long time. At t = 0, it moves to the right position and stays there. Find the initial voltage drop across the capacitor. Okay. So what we're going to do is remember, create the diagram t is less than 0. So t is less than 0. And so when t is less than 0, it's just going to be connected to the left-hand side here. So it's going to be this circuit. And that's what I'm going to draw here. So let me put my source and then my resistor, capacitor, and then my other resistor here. And let's do our current source. How much is in this? We have 10 milliamps. Resistor, we have 10 kilo ohms. Capacitor, we have 400 nanofarads. And the other resistor is 20 kilo ohms. And so now let's think about it. What we have to do is we're going to determine how much voltage is across this capacitor, the initial voltage. That's what it wants. Because remember the equation, I'll keep going back to it. The equation for a capacitor is going to be ice. So I = C and then dV dt. Therefore, the voltage cannot change instantaneously. So the voltage at time 0 approaching from the negative side is equal to the voltage approaching 0 from the positive side here. Okay, that's what we know. So those are the two big things to think about. So we can find the voltage before time is 0, and that will be the same as when it is time 0. So looking at this circuit, we have 10 milliamps and we have these two resistors. And if we recall, it's in this position for a long time. And so whatever voltage is going to be across here, we have to find out. So when I'm looking at this, I remember a capacitor for a long time, it's going to act as an open circuit, if you guys recall that, because it's going to be storing charge across the plates and it's not connected. It's going to act as an open circuit here. And so what I want to draw is another version. Let's look at this. And remember, a capacitor acts as an open circuit where the inductor for a long time acts as a short circuit. So my circuit now looks something like this. And this is our 20K, here's our 10K and our 10 milliamp source. And if you think about it, then all the current is going to be going through this 20K ohm. And the reason being is because this is a short circuit, so there's going to be no current going through. I mean, this is an open circuit, so there's going to be no current going through. And so if we think our current has to be going down here, this 10 milliamps. And therefore 10 milliamps is going down here. 10 milliamps times 20K, what that gives me is 10 e to negative 3 times 20 e to the 3. I got 200 volts here. So I got 200 volts. And since we know there's no current going through this right-hand side here, this is 0 amps, there's no voltage drop across the 10K. So therefore, all the voltage drop must be across this capacitor. And so that means the 200 volts must be across this capacitor. And so what we can do is we know the initial voltage drop is 200 volts here. Reason being is because all the current goes through the 20K and none of the current goes through this 10K since it's an open circuit. So therefore, the entire voltage drop must also be across the capacitor on this side. And so what's the initial energy stored by the capacitor? If we think about that, the initial energy, that'd be W equals 1/2 CV squared. And then our voltage would be 200 volts. And then our capacitance is 400 nanofarads. Oh yeah, sorry, I forgot to. And then do 1/2 times that. So if we look at that, that'd be 200 nanofarads times 200 times 200. I got 40,000. Then I got times 200. I got 8 millijoules. And so that's what I got for part B. So I'm going to write here 8 millijoules. And then find the time constant for time is greater than 0. Okay, that means when time's greater than 0, let me create my other diagram here. So T is greater than 0. And that means it's going to be connected here. We can ignore everything over here. So that means we'll have our capacitor. And then here we have, okay. And at this point, we have a 10K ohm. We have a 50K ohm. And here we have a 75K ohm. And then for a capacitor value, we have 400 nanofarads. And we just calculated, remember, the voltage can't change instantaneously for a capacitor. So initially, what it has is it has that 200 volts here. So I'm going to say V0 is equal to 200 volts. And so what we know here is it wants to know the time constant of the circuit for T is greater than 0. So what resistance does the capacitor see within the circuit? And so the resistance that the capacitor sees is C to 75K, that's in parallel with 50K, and then add that with the series resistor here. When you do that combination, what you get is 50 times 75, and then add 10, 40K. And then we have our capacitor value here, which is 400 nanofarads. And then the time constant is equal to R times C. So that would be 40K ohms times capacitance, which is 400 nanofarads. And just remember the time constant, sorry, I forgot to define tau, is equal to R times C for a capacitor. And so 40K times 400 nanofarads. I got 16 milliseconds. So tau is equal to 16 milliseconds. Okay, so that's what we have here, 16 milliseconds. Part D, write the expression for capacitor voltage via T for T is greater than or equal 0. So at time is infinity, remember that voltage is going to be 0 because all the voltage will eventually, that voltage is going to produce a current, and all that current is going to go for the resistor here and eventually become 0. And remember that voltage can't change instantaneously because of the equation. It's a derivative here, so it's going to slowly give it off and eventually become 0. So the voltage at time infinity, we say, is 0. Okay, remember my equation. If we want to solve for it, it's going to be the final value, which is 0, plus the initial value, which was 200 minus the final, and then times e to the negative t divided by tau. And we calculated tau 16 milliseconds. Okay, yay, we got all that information. So now we can solve for v of t. V of t is going to be equal to 200 e to the negative And what I get for my -1 divided by 16 milliseconds, 62.5. And so that's what I got here. And so that's where t is greater than or equal to 0. Okay.
Yo, I have a quick question. Whenever we do like V infinity or like I infinity, I see how it always goes to 0, and I kind of missed your explanation before. So could you just go over it again?
Yeah. Okay.
Thank you.
So what happens here is that voltage, we know it's going to produce a current that goes through the circuit, because we'll initially have 200 volts here, and then it's slowly, because there's no source hooked up to this circuit now, because originally, remember, we had a source here. So since there's no source providing any current or voltage, it's going to slowly dissipate over time. Think of a capacitor as something that's like backup storage, and it, like, like a backup generator. That's what a capacitor does. So slowly that voltage is going to decrease, because these charges here, the separation of charge, it's going to go off, and it's that current that's going off and providing to the circuit. It's going to go through this resistor, and it's going to dissipate all that. And so it's going to go through the resistor here, and eventually at time is infinity, this will be 0 volts. We can model it by the curve here. That capacitor can only store the charge for a certain, because we initially had 200 volts up here. And so going from the 200 volts, it's going to decline over time and become eventually 0.
I see. So if there's no source connected to it, the capacitor
It's going to
current will
die
always
out and
go to
become
0.
0.
Same as inductors too,
Inductor, it's
or
going to die out and the current will become 0.
okay. So whenever it says to infinity, most likely it's gonna be 0.
Yeah.
Or like always, kind of.
Yeah. So that's a good observation. A lot of the times, it just you'll see. I think that was legit. The majority of them, it really was infinity. If I'm going here, yeah. When I'm looking at all mine, oh, there was one, but that was from his actual lecture where it wasn't. But it was, the reason why it wasn't is because the switch flipped the opposite way. And so there was a source connected then. So at time 0, it flipped the opposite way. And so therefore, it became the initial value for the final value. It flipped it. So that's the only when it's not. So one of them will be 0, either the initial or final. It depends on where the switch flips.
Got you. And that means
Connects the
voltage
source.
and current 0, right?
Yeah, if the source is connected to the circuit, that means you should get a value. If the source isn't connected, it means it's going to go to 0. Does that make sense? If there's no source, it's going to go to 0 for current and voltage. If there is a source connected, therefore it will not be 0.
That makes perfect sense. Thank you.
Then let's go to 7.23. I think this is another capacitor one. Let me look here. Actually, that's exactly the same. I'd rather do 7.25 because that one you'll see. I have a feeling like he's going to question us on that. Oh yeah, I'll do the AP one after. I know 7.25 was one that was in one of his handouts, I believe. Okay. The switch in the circuit in 7.25 has been position A for a long time, and V2 equals 0 volts. At time equals 0, the switch is thrown to position B. So then find these values, and okay, this is when we have 2 capacitors in a circuit. That's why it's interesting. Okay, so going back, what we need to do is we need to draw the circuit at time is less than 0, and then we're going to draw the circuit as time is equal to 0. And so let me draw this out for you guys. So t is less than 0. What is that going to look like? T is less than 0. It's going to be hooked up this way here. So we're going to have 6 milliamps, 5K. And then we're going to have this capacitor. So looking at this, drawing it out, I have here is 6 milliamps. Then here I have 5 kilo ohms. And then over here I have 30 microfarads. Okay, so what we know is the voltage drop. It's been in this position for a long time. So remember, a capacitor is sort of like an open circuit. So all the current is going to be going through this 5K ohms. So just do 6 milliamps times 5 kilo ohms. That will give you 30 volts. Remember, so that 30 volts is going to be across here. And that will be for both the capacitor and that 5K ohm resistor. So 30 volts. Okay. And so that's what we know. So we know the initial voltage on the capacitor is 30 volts. So let's connect it to position B now when time is greater than or equal to 0. So I'm going to draw a new diagram. And T is greater than or equal to 0. What I have here is I have a capacitor. I have another one. Sorry, mine don't look polarized at all. I'm very bad at drawing that. Okay, 2.5 kilo ohms here. And right here I have 30 microfarads. And the initial voltage is going to be 30 volts, as we just calculated here. Because remember, capacitor, the equation, the voltage can't change instantaneously. And then this capacitor is 60 microfarads. And so initially, the voltage here is 0 volts because it was given no supply. And so let's look at this. So the current going through the circuit, now as time is greater than or equal to 0, we know the initial value of voltage for both. If we look at what we have here, let me see, is we can combine these two capacitors, right? Because they're in series. And for capacitors, when they're in series, it's a parallel addition, what you have to do. And so right here is we have our two capacitors, and we're just going to make one large capacitor. And then we're going to have that same resistance value, 2.5 kilo ohms. And when I add those two in series, remember they add for like a parallel combination. So 30 microfarads times 60 microfarads divided by 30 plus 60. And then times 6. What I got is 20 microfarads. And then the voltage, what you do is you just add the two together. And so that'd be 30 volts. So 30 volts here. Let me just put. Okay, we got 30 volts, and then we have this resistance here, so we can calculate the current going through it. And so if we want to calculate the current going through that resistor, 30 divided by 2.5K, I got 12 milliamps. Okay, I got 12 milliamps now going for the circuit. That's what we can determine. And so now we can also from here, it wants these three equations, everyone. So we need to do a special, let's do the current first because the current's the easiest. And so we know the current, like I said, there's no source connected, so it's eventually going to become 0, okay? And so let's just look at the time constant here. Time constant is R times C, so it's going to be 2.5 kilo ohms times the capacitance value, the combination of the two was 20 microfarads. That's going to give me 2.5 e to the 3 times 20 e to the negative 6. I got 50 milliseconds. Okay, so my current at time t is going to equal the final value. In the final value, current we talked was 0 because eventually it's going to die out. There's no source connected. And then the initial value is 12 milliamps. And then minus the final times e to the negative t all over tau, which is 50 milliseconds. I of t is going to equal 12, and then e to the negative 1 divided by 50 milliseconds, that's 20 t, and then this would be in milliamps. That's for t is greater than or equal to 0. Okay, so that's what we got for the current, which is good. We're able to determine that value. Now what we need to do is we need to find the voltage for the first capacitor and the voltage for the next capacitor. And so if we're looking at that in here, the voltage here is V1 here, and then this one's V2, this one on the right. And so the voltage on the first capacitor, because we have two capacitors, you have to use the formula. If you guys recall the capacitor, just use the ice and legit just solve it. So I equals C times dV dt. And multiply both sides by dt. What that's going to give you is I times dt is equal to C and then times dV. And then what you're going to do is you're going to take the integral. And so when you take the integral, what you're going to get here and then versus here, because C is just a constant value for capacitance, you're going to get, if we're solving for voltage, when you do this integral, it's going to be C times, and then it's going to be like V of t. Let me just take that out. Sorry, it's going to look bad. It's going to be, I'm just going to say int for integral of I, and then that'd be dt equals, and then C, and then that's going to be, when you do the integral of this, it's going to be V of t minus V of 0. And then what you're going to notice is when you put that over to the other side, let's see, VT. Yes, that is correct. Divide the other side by 1 divided by C, and then the integral. So integral of I dt. And then that's going to equal Vt minus V0. And add the V0 to the other side, so you can get Vt by itself, 1 divided by C, and then times the integral of t, integral of I, and then dt, and then plus V0. Okay, that's what I got for my V of t. So remember just that equation. You guys have seen it before. It just looks a little weird here, but it's 1 over C, and then the integral of I dt, and then plus V0. Okay, so we can use this equation to find V of 1 and V of 2, because we'll just plug in the values we know for each. And so for V of 1, what I'm going to do here is, we know, so V of 1 of t is going to be equal to 1 divided by the capacitance. Capacitance across that first one is 30 microfarads. And then times the integral of I dt. Well, we just found what I of t is here. And so if we take the integral of that, what we're going to get is, when we do that, let me do the little integral symbol so it makes more sense. The integral of, and then let me type that in there, 12e to the negative 20t, and then that's going to be dt, and then plus the initial value for V1, which we determined was 30 volts. Okay, now when we do that, what we're going to do is when you take the integral, remember all you need to do is you need to pop a negative 1 over 20 in the front. So when you take the derivative, then that negative 20, when it comes to the front, it's the same value. So V of 1 of t, when you do that calculation, what you're going to get, you're going to get 20e to the negative 20t, and then plus 10. You're going to do now for V of 2. In V of 2, it's going to be 1 over 16 microfarads. And then that integral symbol, I'm just going to say int, and then it's going to be 12e to the negative 20t, and then dt. And then plus the initial value, which is 0 on the second capacitor. When you do that and you solve for it, the integral, all you do is that you put negative 1 over 20 in the front. You're going to get V of 2t is going to be equal to a negative 10 e to the negative 20t plus 10. So the only difference here is what you're doing for this problem is it has 2 capacitors. It doesn't just have 1. So therefore, we had to use this equation here, which was the only difference really in it, is we had to go back to this original equation to find the voltage for each of those capacitors. Okay, now that we did that, I'm going to go to the AP, oh wait, sorry, B. The energy stored in the 30 microfarad capacitor at time is 0. So that'd be W equals 1/2, and then times CV, and then squared that voltage. And so what we're going to get is we're going to get 0.5 times, and then the capacitance on that is the 30 microfarad, and then times the voltage originally was 30 volts at time 0, and then square it. What you'll get for your value of energy is, when I did this, I got 13.5 millijoules. Okay, part C. Part C, the energy trapped in the circuit and the total energy dissipated in the 2.5 resistor if the switch remains in position B indefinitely. Okay, so energy trapped in the circuit and the total energy dissipated in the 2.5. Okay, yeah, this one. For the energy trapped in the circuit, if remember, this is going to be going back to our original diagram here. So this one here. So the energy trapped in the circuit is going to be our 2 capacitor values at time is infinity. So if we think about, I'm going to erase this one at time 0 here. At time equals infinity, it's going to look something like this, where we're going to have our capacitor, our other capacitor, and that one resistor value, where this is 2.5 ohms. And here we got 30 microfarads, and then here we got 16 microfarads. And so at time equals infinity, what is it going to be? Okay, look at these equations we just made for the voltage and the voltage here for both of those capacitors. At what, if time is infinity, you're still going to have 10 volts. If time is infinity here, you're still going to have 10 volts. So at time infinity, there's going to be 10 volts across this capacitor, and there's going to be 10 volts across this capacitor. So that's what we're notice. So the energy trapped in the circuit is going to be that energy trapped in both these capacitors. So what I'm going to do is I'm going to do the work in capacitor 1. So the work by 1 plus the work by capacitor 2 is going to be the total energy trapped in the circuit, because energy is trapped in a capacitor or inductive element. And so here, what I get is for this one, I have 13 point, let me just do the quick math on this one. So the work total is equal to the 0.5, 1/2 CV squared, so 30 microfarads times the voltage at time infinity squared plus, and then do the other one, 0.5, and then the capacitance value 60 microfarads times the voltage across it, and then square it. what I got for my work value is, when I calculated that, I got 4.5 millijoules. That's trapped in the circuit. Okay, so that's how you answer all three parts of the question. So what we had to do here is for time is greater than or equal to 0, we had to find how much voltage was stored across the capacitor 1 before we closed the switch. So we did this part of the circuit. We found out how much voltage was across here since voltage can't change instantaneously. Then we calculated the value, found the current going through this part of the circuit. Then we found the voltage for each individual one using this equation here that we remember for voltage. And then we have to use that when we have multiple capacitors. And if we have multiple inductors, we'd use the other equation for that. The energy stored in the 30 microfarad, that was the W equals 1/2 CV squared equation. Then the energy trapped in the circuit, that's as time equals infinity. You have to look at that. And that'd be the energy dissipated in the 2.5 kilo ohm resistors. That would be, if we know from part B, we know how much energy is stored in the capacitor, which is the one element that actually has a voltage across that. Subtract that from the energy trapped in the circuit, and you'll get 9 millijoules that is dissipated in this resistor. And that will be how you answer all three parts of the question. And that should be it for that one. Okay. Hopefully that made sense. Let's go to the problem that Chalkwin said, AP 7.7. Okay, let's try it. So let me clear everything. AP 7.7. In the circuits shown, switch 1 has been closed and switch 2 has been open for a long time. At time is 0, switch 1 is open, then 10 milliseconds later, switch 2 is closed. Find the voltage across the capacitor in between that time interval when it's greater than that time, and then the total energy dissipated. Okay, this one's going to be a good one. It'd be longer. Okay, let's then do, remember what I said is always do time is less than 0. Draw what's happening beforehand. It looks like we're going to have 3 intervals. We're going to have 1 before t is equal to 0, 1 between this, and then 1 when it's greater than. So what I'm going to do here is I'm going to say time when it's less than 0. Let's look at what the circuit is. So it looks sort of like this would be an open circuit here. And this is an open circuit. Oh, wait, no, this would be a closed circuit beforehand. So this would be closed and this one would be open. So we have this part of the circuit to worry about. So when I draw that out here, I'm gonna have my source and I'm going to have I see a lot of resistors. I know we're gonna have to combine those. And then we have our capacitor. 60 kilo ohms. Then here we have 40 kilo ohms. And over here we have 25 kilo ohms. And here we have 1 microfarad. Okay, remember a capacitor has infinite resistance since the plates are not touching, the plates are separated. And so therefore there is a gap. A gap means that there's infinite resistance since we don't want charge going from one side to the other. So there has to be a voltage across the capacitor. So we're going to have infinite resistance. So when we have infinite resistance here, infinity times 25K all over infinity plus 25K. Just, you can do this on your own calculator. 99999 times, and then do your capacitor value 25K, and then divide that by, how many nines did I use? 1, 2, 3, 4, 5, 6, 7. Okay, divide that by 99999, and then add 25K. And what you're gonna get is it's gonna be about 25K. Is gonna be your result. So then 25K plus 60K in series, and then do that with the parallel combination of 40K. Get your equivalent resistance. And so then we'll have it. So then we can calculate how much is actually going through. So we have 10 milliamps here. And then for equivalent resistor, we have 60. And then 40, what I got for my equivalent resistance was 27.2. 27.2 kilo ohms. Okay, so now we know how much resistance, so we'll know the voltage drop through here. And so the voltage drop we're going to be having for the circuit is this value, 27.2 kilo ohms, and then multiply that by 10 milliamps, got 272 volts. So that's how much we have throughout our circuit for the voltage. Okay, let's look now, let's divide it up and let's try finding the voltage across that capacitor. So let's go left to right within our circuit here. So let's find out how much current is going through here. If we know there's 10 milliamps going through here, and therefore we have to find out how much is going through each of these. And so if we remember 25K plus 60K, that was 85K. I did that right. 85 e to the 3 times 40 e to the 3. 85 e to the 3 40 e to the 3. Yeah, okay. So what we need to do to find the current going through the 60K is the current from the source, which is 10 milliamps times the resistor you're not interested in, which is this 40K, all over the resistor you're not interested in, plus the equivalent resistance. So 40K plus the equivalent resistance. So whatever's to the right there, we had 85K. And therefore, we know how much current is going to the right there. So 10 milliamps times 40K divided by 40K plus 85K. I got 3.2 milliamps here. So 3.2 milliamps going to the right here. And therefore, if I have 3.2 milliamps here, I'm just thinking about it. I'm like, how much then is going to the right here and how much is going down? Well, we know that there's going to be infinite resistance here to the right, correct? So all that current is going to be coming down here. So that's 3.2 milliamps is going to be coming downwards. And therefore, we need to find the voltage drop across this 25K ohm, because that's going to be equivalent to the voltage drop across this capacitor. So what I'm looking at here is the voltage drop across the 25K, multiply that by the 3.2 milliamps. I got 80 volts. So between these two, what we have is here, we got 80 volts. Yay. Okay, so we found the voltage at the capacitor before time is 0. So now let's do the next interval. So the next interval, what we're going to have is 0 to 0.01 seconds. Looking at this, that would mean this would still be open, but this would be open as well. So what we have is just this part of the circuit here. And so I'm going to state that this is 0 equal 0.2, which is equal between 0.01 second. Okay, what we're going to draw for a circuit is we're just going to have this 25K ohm and then this capacitor. Oh, that's a really bad capacitor. I'm just going to draw it this way. Sorry, I'm not going to draw the polarization. So this is our 25K. And this here is our 1 microfarad. And we found out how much voltage was across it. It was 8 volts. And so we can have that here. So let me just add the plus minus and then say 8 volts. Okay, so what's going to happen in between this time frame is we're going to have to calculate the voltage. So we know the voltage initially, which is great. So our V of t the final, okay. One thing, Dr. Ari, I had to ask him in office hours. He says for the final, always assume in this time interval, it is going to be infinity. So if it was infinity, that means the voltage would be 0 plus, and then the initial was 8 minus 0, and then e to the negative t divided by tau. And if we look at tau here, it's r times c. You guys know that by now, probably. So R times C, 25K times 1 microfarad. Times 1 microfarad. I got 25 milliseconds. V of t is going to be equal to 8e to the negative 1 divided by 40. Okay. That's what I got for my voltage between this time interval. So 0 and then equal to t. And then that'd be okay, 0.01 seconds. Okay, so that's what we got for our value right here for VC of t, 80e to negative 40t. And then that's correct, and we noticed right there. Now we can check time is greater than or equal to 0. So that means in our circuit, what's going to happen is, let me see, this is going to become shut, and then we're going to look at this part. Okay, so time is greater than or equal to 0.01. What's going to happen there is we're going to have this 25K, going to have the capacitor, and we're going to have 100K. Oh my word, I just need to have a whiteboard, an actual one. This is so sad. Okay, 25K and then 100K. At least I don't write as bad as some people, so you guys should be happy about that. 1 microfarad. And then let's see, what we have here is, I'm looking at this, it wants to know the voltage. Okay, so this part, we have to find it initial and then the final. We for sure know the final is going to be 0 as well. What we can do, okay, this is the part where I can see you could get tricked up. We found the equation right before, correct? That was good at that time interval for the voltage. So let's just plug in 0.01 second in here to find the initial voltage. So V of 0.01 is going to equal 8e to the negative, and then that'd be negative 40 times, and then the time would be 0.01. What I get here, 8e to the negative 40 times 0.01. I got 5.36 volts. Okay, so I got 5.36 volts here at time 0. So when I'm trying to make this equation up here, I definitely know for sure the final voltage is going to eventually be 0. We know that. Plus, and then the initial would be 5.36 volts. And then minus the final, that would be, wait, 5.36, could I? 0.01, wait, 80, let me check something real quick. 0.01 times 40. 53.6. That's where the issue is coming in. 53.63. I just multiplied that wrong. Minus the final, which is 0, and then times e to the negative, and then t divided by tau. So here to determine our tau value, what we have to do is, you can see those two resistors are in parallel. So the equivalent circuit is going to be the one resistor and then the capacitor. So 25 times 100 divided by 25 plus 100. I got 20K. One microfarad here. R times C, so 20K times 1 microfarad. That's going to give me definitely in the milliseconds, if we just think about it. So 20 milliseconds here. Okay, and then let's do the equation. Let's sum that up. So V of t is going to equal 53.63, and then that'd be e to the negative, and then 1 divided by 20 milliseconds. That'd give us 50t, and then that'd be in between that time interval, everyone. So that'd be the t is greater than or equal to 0.01 seconds. Okay, checking out e to the negative 50t. Okay, one thing to remember though, remember this is offset. And since it's offset, that's a good point to bring up. This t here, remember this value is offset by 0.01 second. So what I like to write here is always where t is equal to t minus 10 milliseconds, because it's offset by 10, sorry, by, I'll just do, to keep it just normal, 0.01 seconds. That's what it's offset by. So if you actually want to write the v of t, the correct equation for the time, 53.63, and then e to the negative 50 times, and then that would be substitute in what you have, t minus 0.01. Okay, so 53.63 e negative 50 t minus t. Yes. Okay, that's what we have here for v of t. And therefore, we got parts A and B. Okay, looks like we got a question up here. 80E. Is it supposed to be 80E? Yeah, sorry. I forgot that 80. Sorry. Let me fix that real quick. There we go. Okay, so here, sorry. 80 volts. I just forgot the 0 at the end. This should be 80 here, 80, then 80. Good job. Good eyes. Okay. And then the total energy dissipated in 25K ohm resistor. So the total energy dissipated, and then the total energy dissipated in the 100K ohm resistor. Okay, this one is definitely going to be the harder one, I know, because the total energy dissipated, that would mean how much as time goes to infinity, how much is stored in that capacitor, and then we would take the total energy calculated at time 0 and minus that from how much is left in that capacitor as time went to infinity. And so what we're going to do here is, let me pull this up just to make sure I don't want to make any errors on this for you guys. 7 points. Because it was a weird one, I recall. So okay, so we have to do 2 time intervals across this resistor. So from 0 to 0.01 and 0.01 to infinity. And so what I'm going to do here is the energy in this 25K ohm resistor is going to equal, and then the interval from 0 to 0.01, and I'll tell you why I'm using an integral here. And then it's going to be the voltage, and then square this divided by resistance. Okay. And then this is d of t, and then plus, don't worry, it looks weird right now. Trust me, won't be as bad. V c of t, and then okay, and then the other interval would be from 0.01 to infinity, correct? Those were the 2 intervals we had. And so this would calculate the power in, oh, sorry, I forgot the square here. The power, if you guys remember, work equals, sorry, P, man power is work per unit time. Therefore, if we move it over and take the integral to solve for work, what we get is we get work is equal to the integral of P dt. So that's what we get for equation, and power is IV I squared R, or V squared over R. Since we know the voltages here and we know the resistance value, that's why I use this form. Okay, so now that I know that, I'm going to plug in what I got for my values. So this is going to be, okay, I'm just going to pull up, honestly, to make it simple. Let me just clear all this on the right-hand side real quick. Because doing integral calculator, just so you guys can see calculator symbol lab. Symbol lab. Yeah, okay, just so it looks cleaner. Okay, what I have here from 0 to 0.01, that's going to be my voltage on top and then divided by the resistance value. Since it's asking for the 25K ohm resistor, we know that's down here, so 25,000. The voltage on top is going to be 80 e to the negative and then 40 t. I'm getting that value from the first one up here, this interval. We solve for a here. And then I need to square that. So square this. So let me put this inside. All right. And then do dt plus, and then the other interval here, which is 0.01 to infinity. So let me do, and then go to infinity. And then the equation for this is going to be from part B. And so the equation from part B we got was 53.63 e to the negative 50 times t minus 0.01. And then square that. And then when we hit go on this, what it should give us for value is we're going to look down here. And we got 2.9 millijoules, 2.91. That matches up with part C. Let's do part D. So part D, the total energy dissipated in the 100 kilo ohm resistor. Well, if you notice the 100 kilo ohm resistor, it doesn't take effect in the circuit till the 10 milliseconds. So we're only going to have to do the one side of the equation. So for this one, it's only this, but it's 100 kilo ohms. So 100 kilo ohms, and same equation. When we calculate that, what we get is we're going to get the answer of 0.29 millijoules. Okay, so that's how we got part C and D. Hopefully that made sense a little better. Just you have to take, remember your power equals dw dt, and you can take the integral. I'm sure Dr. Ari has something a little easier than that, but that's how I saw it from parts A and B using the equations we calculated. And then you just found the energy from those. Okay, now that we talked about those, are there any other questions you guys are confused on the homework about? Were you guys good? Any other?
I haven't really looked at like the 7.78 or 7.8. I don't know if I should, because those are probably gonna be oh no, I'm talking about 7.80 on the CP questions.
Oh,
but 7.8 looked like a little different too. Oh Jesus.
I feel like that's how all of us react. Okay, we'll do 7.80. Okay.
No, we could just go back to 7.8.
Oh, okay. We'll do
Yeah,
7.8.
I'm not even
Then
gonna look at that.
okay.
Look, they had 4 switches in the other one.
Oh, here it is. Okay, 7.
Oh yeah, perfect. Yeah, let's do that one.
Switch A in the circuit has been open for a long time. Switch B is closed for a long time. Switch A is closed at t equals 0, and after remaining closed for 1 second, it's opened again. Switch B is open simultaneously, and both switches remain open indefinitely. Determine the expression for the inductor current and when is valid between those two time intervals. Okay, let's talk about this one. Woo-hoo. I think everyone else in this room, Tuan and Joaquin, are just like, okay, we're done. Okay, switch A. So let's look at this circuit right now. So it says at time 0, this is going to shut. So this is an open circuit before. So looking right here, let's look at this part. That's at t is going to be less than 0. So when I'm looking at this, I remember I was confused on this. Sorry, this is going to be the interval between 0 and 1. So let me actually rephrase that. So t between 0 t equal to 1. Okay, so if we look here, the current source, if there's a short circuit right here, all the current is going to be going through that short circuit, correct? Because why would the current want to go through resistance? It could go through way easier path. So all the current's going to be going up through there. So that source isn't going to affect anything down here, which is sad because like nothing's then happening from that source. And so if we looked at the circuit, there's going to be 0 current going through here because there's all the current's going to be going up through this short circuit up here. So what I can say is between 0 and 1 second, I is 0 for this. So I'm just going to draw it here, just giving you that little diagram. You just have the inductor, you have the 3 ohm resistor, then you have the 6 ohm, and then you have like that right here, 9 ohm. I'm not going to include the current source because all the current's going through there, but this is basically what it looks like, and you had no initial current going through here. So therefore the current remains at 0. Here we have the 3 ohm, here we have the 9 ohm, and then here we have the 6 ohm. Okay, now that we got all that, let's look at the next time. So if we know that, let's look at time is 1, because at time 1, this is going to open. So we were able to determine, this one was everything right before, so maybe I shouldn't include this because the switch opens at time equals 1. So this should just be time is less than 1. So this is for time is equal to 1. What's going to happen is then that is now going to include this current source because now this is going to become open. So what's going to be available is, oh wait, oops, I totally messed up here. This was at, yeah, wait, sorry. I messed up in this. This was actually for time is less than 0. Because then at time is 0, this shuts here. So let's look at that interval once again. Sorry, you guys, I make errors too. So here we go. So at time equals 0, this becomes shut. And therefore, there's a source now connected. And so some current's going to be going through here. So let's look at that interval. So 0 to t and then to 1. And I'm not going to include 1 in here. So we have this 10-volt source. And then we have this resistor, 2 ohms. Have this 0.8 ohm. We have this 3 ohm. Have this 2 Henry. Have this 3 ohm here. And then we have this 9 ohm, and I'm not going to include that current source because all that current is just going to be going through this switch here. So it's literally going to have no effect here. And then if we think about this, this would be like infinite resistance here. And then for a current source, we represent it as an open. And then so then here, what we're going to have. So let me, wait, it'd be a short actually. Let me pull this. This is a good one. All current goes for the shorts. So what we're going to have here. Okay, yeah, because this is a short here. What that's going to do is the equivalent resistance of all this. I had to go back to my notes for this one. Hopefully it circles that. The equivalent resistance of all this guy, because right here, if that's a short circuit, then everything is just going to be modeled for equivalent resistance at just that 0.8, so the 2 Henry. Yeah, that causes all of this guy, because if you think about it, if you have a short, that means there's 0 resistance here. So this would be 0 ohms. Because right here through this path, if we look at it here, there can be 0 ohms of resistance. And so that's why it causes this to become 0 ohms. And then combining that with the 3 times 0, so this becomes all 0. It's really weird, but
I honestly don't understand that at all.
okay, let me try repeating. It is so strange. Okay, let me go really slow through this. Okay, since we have a short right here, that means there's 0 resistance through here. So if there's 0 resistance, and we notice through this entire branch, we can have, that means the equivalent of this, because they're in parallel, correct? All these 3 right here, that means this parallel combination, if you even try doing 9 times 0 divided by 9 plus 0, you're going to get 0 ohms. And therefore, we have 0 ohms right here. And what I did after that is looking down here, then we have a 3, and then we have a 6, and then we have 0. And so then we have a 3 and a 6 here. And let me see. That would then be the parallel combination of the 2. So 3 times 6 divided by 3 plus 6. And when I do that, 3 plus 6. Kato, taking this problem. Okay, this would be 2 ohms here. And so our equivalent would be 2 ohms. Okay, hopefully that makes sense. So here we have a short, but because these are all in parallel, it's going to cause there just be 0 ohms. So we have 0 ohms right here. And then 0 plus 6, that would be 6. And then we have that in parallel with the 3. And that would mean we have 2 ohms, therefore. And so in our diagram over here, what I'm going to draw for this part is I'm going to draw 2 ohms over here. So 2 ohms. And then over here in the top resistor, I have 2 as well, 0.8 here, just copying from the diagram, 3, and then here I have 2 Henrys. And then I have a current coming down. And so when I'm looking at this, trying to evaluate what I should do next, I had this 10 volt source, I have all this. I'm gonna have to look at the final plus the initial minus final. So let me try simplifying this. So what's going to happen here is we have to look at the current supplied going to the inductor with just time in finding that out. So we need to find the final current, and we have to find what that be, because initially there was 0 current, we know, going through the inductor because that current was going through the source and this wasn't connected. But now we have a source connected. So here we had I through the inductor was 0. But here we're going to find when it's hooked up, what will it be? So if we look at this, what we're doing right now is we have to determine how much is coming. So how much resistance does this source see? So if I'm going to draw this, this is what the source is seeing right now. It's not going to see the inductor. So it's going to see this 2 ohm. It's going to see this 3 ohm. It's going to see this 0.8. And then this will act as a short because it will resist any change in current. So initially it's going to see nothing here. So 0 times 2 divided by 0 plus 2, that's going to just be 0. So I'm going to draw a straight line here. This is 3 ohms. This is 2 ohms. This is 0.8 ohms. Okay, the 0.8 is in parallel with 3. So 3 times 0.8 divided by 3 plus 0.8. And then plus 2, because that's in series. I got 2.63 as my equivalent resistance. Okay, 2.63. Okay, now that we know that is our equivalent resistor and we know our source was 10 volts, what we have is we can find the current. So 10 divided by 10 volts divided by resistance, that gives us the current. So we get 3.8 amps. Okay, everyone, we got 3.8 amps going through. That's good. Now what we need to do is we need to determine how much is going through each branch. So we know 3.8 is going through here. And let's see how much is going down and how much is going to the right. So how much is going down into the right here? We want to find how much is going through the inductor. So let's focus on what's going to the right. So if I'm going to calculate that, I have to look at I, do some current division, is equal to the current coming from the source, which is 3.8 amps, times the resistor we're interested in, which is, if we look here, it was 0.8, because these two, it just sees as 0 for this, and then the parallel combination be 0, so it's just 0.8. Oh, sorry, the one we're not interested in is on top, so this would actually be the 3 all over the one you're not interested in, plus the 0.8, which is the one you're actually interested in, the rest of the resistance to the right of the circuit. Okay, when I did this, 3.8 times 3 divided by 3 plus 0.8, I got 3 amps is going to the right here. So this is 3 amps. And then the other 0.8 amps is going down here. Okay. And so if we have 3 amps, it's going to go through the path of no resistance. So it's going to go through this inductor. So 3 amps right here. Because if we remember our inductors for a long time, over time, they become no resistance and they're just a short circuit. And so we have 3 amps going through here at the inductor. So if we do our current equation now for this time interval, what we're going to get is we're going to get I of t. Remember the final value I told you guys is 3 amps plus the initial value, which is 0, minus 3 amps, the final value. And then times e to the negative t divided by tau. What's tau here in this case? Tau is equal to R time, L divided by R. And L divided by R is what does the inductor see for the resistance? We need to draw this now without the source in order to calculate what resistance the inductor sees. So we have that 2 ohm up here, we have the 3 ohm, then we had the 0.8 ohm, then we have our inductor here, and then we had the 2 ohm. Okay, let me do this. So this would be 2 ohm This would be 0.8 ohm. This would be 2 ohm. And here we go, 3 ohm. Okay, so what does the inductor see? Well, we know this 2 ohms in parallel with this 3 ohms. So I'm going to do 2 times 3 divided by 2 plus 3. I got 1.2. Add that to 0.8. I got 2 ohms here. So I got 2 ohms here. Then I got the inductor. Oh, sorry. And then 2 ohms. I made that pretty small. So we had 2 ohms and 2 ohms here. They're in parallel. So 2 times 2, 4 divided by 2 plus 2, 4. That'd be 1 ohm. So what we got for our equivalent is we got this inductor and we have a 1 ohm resistor. Yay. Okay, we got that. And our inductor value is 2 henries. So our L divided by R, that'd be 2 divided by 1. So our tau value here would be 2. 1 divided by 2 is negative 0.5. And so when we calculate this final value here, it's going to be 3 minus 3. And then this one is e to the negative 0.5t. And then that would be between 0 t and 1. Okay, that's how we calculated this one here. And then we're going to move on to part B, which is above or at 1 second. And so now we're going to do that. So at 1 second, let's look what happens. Okay, so I'm going to draw that over here. So at t is greater than or equal to 1, what is our circuit going to look like? Let's look at the left-hand side and let's evaluate. So at 1 second, it's going to open here. So we're no longer concerned with this part. 1 second, it's going to open here. So therefore, the current source is going to impact. So this is what we're looking at as our circuit. So we're going to have our inductor. Then we're going to have our resistor. Oops. Let me draw this more down. Got another resistor here. Then we got another resistor here. And then we have a current source. And then that's the infinite resistor. So I'm not going to include it because infinity times 9 divided by infinity plus 9 is just 9. So I'm not going to include that top latch there because it opened up. Okay, and then now I'm going to label 2 henries here for inductor. We got 3 ohms. I'm just going to put 3 here. We got 6 ohms here. We got 9 ohms here. Okay, so there we go. So let's try finding out what this 8 amps does. Okay, so I'm looking at this here, and we know initially how much current was going through at time was 1 second. Well, we can find that out the initial value. Just plug in literally t equals 1 here. So our value for part A, so 3 minus 3 times e to the negative 0.5. That'd be at I1 is equal to this. And so when I do that, 3 minus 3 e to the negative 0.5. I got 1.18. Wait, let's see. 3 minus 3 e. Yeah, that's what I got for my value. So that should be 1.18. Just so we know our initial value here. So what we know for the current going down through here is 1.18 amps. And that's just at time 1. Okay, so we see we have a source going through here, and we want to see how much of that current is going to actually go through the inductor in order to find the finalized current. And so when I'm looking here, what I'm going to see is let's find the equivalent resistance. Since it's going to be in this position for a long time, since it's going to go to infinity, this is going to become a short circuit, our inductor, whereas a capacitor would become an open circuit. But therefore, we can calculate the equivalent resistance. So 0 times 3 divided by 0 plus 3, that's 0. So what I can do is I can re-represent this. Then we have the 6 and 9 ohm, this current source then. And looking at this 6 is in parallel with the 9, correct? Because they share these two nodes right here. So 6 times 9 divided by 6 plus 9, 3.6. So I have my current source, and I had 3.6. Okay, everyone. Now that we know the resistance here, and we know the amount of current, let's go back and let's try finding how the current would divide throughout the circuit in order to give us the current we want to find going for the inductor at time infinity. Okay, so looking at this, what I'm seeing, because this is the current initially at time 1, I'm going to say, but time equals infinity, we want to see how much it's providing to the source, from the source to that inductor. Okay, so if I'm doing current division here, we recall that in order to find the current going down here compared to the current going through here, I'm going to set up my equation here. So I'm going to say I is equal to the current coming for the source times the resistor we're not interested in, which is the 9 ohm, divided by the resistor we're not interested in, plus the rest of the resistance, which was just that 6 ohm. If we look at the diagram below. And so what I got for my current going down here was 8 times 9 divided by 15. I got 4.8 amps. Okay, so we got 4.8 amps going down here. How much of that is going to go through an inductor and how much is going to go through the 3 ohm? The inductor will become a short circuit, so that means that the 4.8 is going to be going to the left, where 0 amps will be going for the 3 amp at time infinity, since this will become a short circuit, since there will be no change in current with time. And so 4.8 amps is going to go through here. And so that will be at time infinity, I'm going to say it's going to equal 4.8 amps here. And now I'm going to write an equation for current. So I of t is going to equal, and remember this is a 1 second delay, so I'm just going to put an asterisk in here. And the initial value was 1.18. Sorry, the final value. It's final plus initial minus final e to negative t over tau. So final value is 4.8 in the opposite direction of what it had in the diagram. See how it's going down, but the 4.8 is going up here, plus initial 1.18 minus, and then that'd be a double negative, so that'd become a plus, and that final was 4.8, and then e to the negative t asterisk over tau. We have to determine what tau is, where tau is going to be L over R. And now we have to see how much resistance does that inductor see. And so we have to draw the diagram again with just the inductor. And so if we do that, we'll get this. I'm just going from this diagram over here. This blue one, inductor sees 3 ohms, sees 9 ohms here, and sees 6 ohm here. And it ignores the source. And so let me see. That is true. So the resistance seen by it would be Yeah, that opens. That's all correct. Okay. What I'm going to get is, I'm just trying to think, is this 9 ohm? If the current for the source, that would be 0. Yeah, okay. The interesting part here is, remember how we have this current source here? So the resistance seen, a current source, if you remember, it is a short where a voltage source is an open because there's a voltage potential across the two, where a current source, it just goes through. So therefore, a 0 in parallel with a 9 ohm, that creates a short here. So we have a 3 ohm and we have a 6. And so 3 times 6 divided by 3 plus 6 is 2 ohms. Oh, okay. So got my inductor, and then I have 2 ohms here. And so 2 ohms, the inductance is 2 henries. So 2 henries divided by 2 ohms, that's 1. So 1 for our tau. And so if our tau is 1 here, I'm going to put in 1, that would mean that our equation is going to be, and let me just do I, still that T apostrophe, is equal to negative 4.8 plus, and then that's going to be 5.98 e to the negative t divided by our tau is 1. Sorry, so then just keep it this way. But where t hyphen equals t minus 1, and that would then make our equation I of t is equal to negative 4.8 plus 5.98 e to the negative, and then the negative would be placed in there, that'd be t minus 1. Okay, but I'm looking at their equation, t minus 1, they got 1.25 for the time constant. Let me see, what did I mess up? I messed up something here. Resistance seen is 2.5 at time is equal to 1. How did they get that for their tau? That opens, so you don't see that, but you see 0, then that opens, so that would be 3 times 6, 5 by 10 plus 6, 2. Let me see how they got that. Everything else in the equation's right. It's just the tau value. The tau looks like, okay, here. Okay, because it'd be, does that mean 9? So that'd be 9 times. Wait, let me look. 6 plus 9 times. So plus 3. No, that'd be 2 point. Okay, I see how they did it. Here, the current source, they didn't treat it as a short, sorry. So they treated it, so they just had, you ignore the source, I guess, in total. Just don't even take it into account here. So keep that 9 ohm here. So 9 plus 6, that's 15 in parallel with 3. When I did 15 times 3 divided by 15 plus 3, I got 2.5 ohms here. So my tau became 2.5, not 1. And because it became 2.5 in this equation here, when you do 1 divided by 2.5, I got 400. I did 2. Yeah, when your tau then becomes 2 henries divided by that 2.5 ohms, you're going to get 800. Sorry, this is looking really bad right now. This you're going to get 800 here. And so 800 milliseconds. And 1 divided by 800 milliseconds, what you're going to get is 1.25. So 1.25 is going to be in front here. So just insert 1.25 in front of that t value here. And then that's why here they had a negative 1.25. Okay, So this is where the 1.25, insert that in down here. Okay, hopefully that made sense. And I probably just made this, hopefully that was a little helpful, at least, Kato. I'm sorry, I probably lost you throughout that. Okay,
Oh no, you're good. You're good. Can you just leave that page up for a second?
yeah, and then I'll clear it. I'll end it here unless you guys have any other crazy questions, but hopefully that helped a little bit. Just what I said is do my diagram style, do when time's less than 0, then do the time interval, you guys, and then see what happens. And then remember Eli the Iceman, that's going to help you. And remember the biggest equation of all is x of t equals final value plus initial minus final e to the negative t over tau. And those are the big takeaways from the lesson. So hopefully that was good. And I'll pause the recording and